Assalamu alaikum everyone. This is the second lecture on series resonance circuit of EE212, and in the last lecture we started from the definition of resonance circuit, and we talked a little bit about the resonance phenomena. And by resonance, if I have to define the resonance, it is a phenomena at which the response of the circuit is maximized, and that response can be a current or voltage gain. There are two different type of resonance circuits. The first one was series resonance circuit, and the second one was parallel resonant circuit. So then I briefly explained about the series resonance circuit. And in series resonance circuit, the resonance occurs when XL is equal to XC. So this was the inductive reactance and this was capacitive reactance, and at resonance the impedance was purely resistive. So if the impedance was purely resistive, the current in the circuit was maximized, and the power factor was unity because the voltage and current are in phase. So the theta z, that was the angle between voltage and current, that was 0. So the power factor was unity. Secondly, I explained a little bit about the quality factor. So actually the quality factor, it just defines the sharpness of the gain. The larger the value of the quality factor, the greater will be the sharpness of the gain. And if it is a smaller value, the gain curve will flatten out. And the second term that I explained was bandwidth. So bandwidth is the range of the frequencies for which the power of the signal is at least half of the maximum power. So it is range of frequencies for which the signal power is at least half of the maximum power. So these were the two terms that we defined, and the bandwidth is actually bounded by two different frequencies. One is omega low and the other one is omega high, and these two frequencies occur when the gain value is 1 over under root 2 times the value at which the maximum power of the signal occurs. So that's the brief overview of the last lecture where we discussed about the series resonance circuit. So now today we will be deriving the equations for the lower and upper cutoff frequencies. So if I'll just write it down, so these frequencies omega L and omega H, you actually call them cutoff frequencies, or you can also call them 3 dB frequencies. And also the corner frequencies, half power frequencies, so all of these cutoff frequencies, 3 dB frequencies, corner frequencies, half power frequencies, all of these are the name that we can just call omega L and omega H with. So starting from basic circuit of series resonance, it is the series combination of resistor, capacitor and inductor will have a voltage Vi, and then there is a current that is passing through the impedance of all the individual elements is same. Now if I had to find the voltage across the resistor V naught, so we can simply apply the voltage division rule. So V naught is equal to R over R plus J omega L minus 1 over omega C into Vi. So we have applied the voltage divine rule. So the element across which we have to find the voltage is in the numerator and the total impedance is in the denominator. If I'll take this voltage value, the input, on the other side of the equality, that will be R over R plus J omega L minus 1 over omega C. And if I take this resistor in the denominator, that will be 1 over 1 plus J omega L over R minus 1 over omega R C. So this term actually is known as voltage gain. So this is the equation of your voltage gain for a particular series resonance circuit. Now if I denote G J omega is equal to V naught over Vi, this is your voltage gain, so I have just represented it with G J omega. This is your S. Now if I have to find the magnitude of G J omega, so it is equal to real part of the gain square plus imaginary part square under root. So this will give you the magnitude of the gain, and if I have to find the angle of the transfer function, that will be tan inverse imaginary over real part of the gain. So now from equation 1, if I have to find the gain magnitude, that will be gain magnitude will be the numerator magnitude is 1 and denominator magnitude will be 1 square omega L over R minus 1 omega R C square and under root. So that will be your gain magnitude, and if I have to find the angle or phase of gain, that will be the angle of numerator, that will be 0. The denominator will be tan inverse omega L over R minus 1 over omega RC divided by 1. And if I have to take this numerator in the denominator in the numerator, that will give you the gain value, the phase of the gain equal to 0 minus tan inverse omega L over R minus 1 over omega RC G J omega. So this is your phase of the gain, voltage gain equation. And if you have to find the magnitude, so this equation A will be the magnitude of your voltage gain. So now if we will draw the equation A and equation B, it will be represented by these two curves. For the first curve, this is the magnitude of the gain and it just represents a band pass filter. If we know this omega low and omega high and we define them, this particular series resonance circuit that shows you that represent a band pass filter, because all the frequency values that are before omega low and after omega high, they will be filtered out, and only the signal values for the frequencies between omega low and omega high will give you some output, and the maximum power will be at omega naught. So this just represents a band pass filter. Now if we have to find these two frequencies, the cutoff frequencies or the half power frequencies, we have to use a formula that we already know. We know that the half power frequencies they occurs when the gain value is 1 over under root 2 times the value at which maximum power occurs. So what does it mean? So if we have a voltage V at which P maximum occurs, then for P half it will be V over under root 2. So I have proven that in the last lecture. If I have to write it down, V naught over Vi magnitude will be 1 over under root 2 times 1, and 1 over under root 2, 1 over 1 plus omega L over R minus 1 over omega RC square under. So this is the same value that we calculated in equation A. So the same value that we calculated in equation A. Now if I have to solve this equation, this will be so I've just solved the equation. First I have taken the square of this particular equation, and after inverting the equation I got 2 is equal to 1 plus omega L over R minus 1 over omega RC square, and after taking this one to the other side of equality, it will become 1 is equal to omega L over R minus 1 over omega CR. If I have to remove this square value, I have to take the square root. It will give you plus minus 1 is equal to omega L over R minus 1 over omega CR. So this is the equation that we will be dealing with in the later part of this lecture. Now we know that for omega less than omega naught, XL is less than XC. And from the last lecture, XL is equal to omega L. If omega L is a smaller value, XL will be a smaller value. Similarly for XC, it is 1 over omega C. Omega is a smaller value, XC will be a larger value. So XL is a smaller value than XC. So we can say that VL is a smaller value than VC. Then the equation, for example, A will be 1 is equal to omega L over R minus 1 over omega CR, and this one should be negative because XL is less than XC. So if this value is less than this value, then the whole term will be a negative value. So if I'll just simplify this one, this will become minus R is equal to omega L minus 1 over omega C. So this was the first case, and in the second case, if omega is greater than omega naught, so XL will be greater than XC and VL will be greater than VC. And if XL is greater than XC, then the equation A will become 1 is equal to omega L over R minus 1 over omega CR, and the finalized equation will be R omega L minus 1 over omega C. So now we have two equations, one for omega less than omega naught, that is, you can call it 1, and the second equation for omega greater than omega naught, and you will call it 2. So if we have to solve equation number 1, we can write it like omega square LC minus 1 plus omega RC is equal to 0. And if I'll take LC common from the first term, it will be omega square is equal to omega square plus omega R over L minus 1 over LC. So this is your quadratic equation. So we can solve it by using quadratic formula, omega is equal to minus b plus minus under root b square minus 4ac over 2a. And we know that a is equal to 1, b is equal to r over l, and c is equal to minus 1 over under root lc. So if I'll put these constant values, particular equation will get omega is equal to minus r over 2l plus minus under root r over 2l square plus 1 over lc. So now if I have to solve this by putting all the values, that will be minus r over 2l plus minus 1 over 2 under root r over l square plus 4 over lc. So after putting the constant values in this formula, I got this equation, and by taking this 1 over under root 2 inside the square root, that will give you this equation. Now this equation we got it for omega less than omega naught, so this will be omega low, and for this plus minus sign, the frequency values are always positive, it cannot be negative. So the final equation will be omega low is equal to minus r over 2l plus r over 2l square plus 1 over lc. So this is your final equation if you have to calculate the lower cutoff frequency by using the elements of the RLC circuit: resistor, inductor, and capacitor. Similarly, if we solve the equation for omega greater than omega naught, we will get the final equation for higher cutoff frequency: omega h is equal to r over 2l plus r over 2l square plus 1 over lc. So we have two equations, one for the lower cutoff frequency and the other one for the higher cutoff frequency. Now we also know that the resonant frequency omega naught is equal to 1 over under root lc, and the quality factor it is equal to omega naught l over r is equal to 1 over omega naught rc. Now if I'll put these two equations in the above equations, we can have another equation for the lower and higher cutoff frequencies, which will be omega l is equal to omega naught under root 1 over 2q, where q is the quality factor and omega naught is the resonant frequency, plus 1 over 2q square plus 1. Similarly, for higher cutoff frequency, omega naught 1 over 2q plus under root 1 over 2q square plus 1. So if for a particular circuit, if you know the resonant frequency and the quality factor, you can easily calculate the upper and lower cutoff frequencies. Now if you have to find the bandwidth, from the definition of bandwidth, it will be equal to the higher cutoff frequency minus the lower cutoff frequency. Actually, bandwidth is just the range of frequencies for which the power of the signal is half of the maximum value. So it is bounded by the lower and upper cutoff frequency, so all the frequencies within that particular band is considered in the bandwidth. So if we have to define it, we'll just subtract the lower cutoff frequency from the higher cutoff frequency. It will give you a range of frequency that is included in the bandwidth. So from the equations, above equations, which are these ones, we call them B and C. So if we'll just subtract omega h from omega low, that will give you omega naught over 2q plus omega naught over 2q, and the final value for bandwidth will be omega naught over q. So from this relationship, we know that bandwidth is inversely proportional to quality factor, right? And what does it mean? So if we have a signal with high quality factor and then we have another signal with a low quality factor. So this is Q1 and this is Q2. And for this quality factor, for the curve Q1, we have half power frequencies somewhere here, 1 over under root 2 of, for example, VQ1, and for the second one it will be 1 over under root 2 VQ2. So it will have a larger bandwidth. So this is the bandwidth 2. And for this one, the bandwidth is very small. So what does it mean? That the circuit 1, which has a quality factor Q1, is more selective because it allows only a very small frequencies for which signal can pass through the circuit and we can have some output. But for the second curve, whose quality factor is Q2, the bandwidth is very large, so it is not very selective and it will allow a lot of signal. So if the quality factor increases, the bandwidth decreases, and if the quality factor decreases, the bandwidth increases. And with the increase of quality factor, the series resonance circuit becomes more selective, or in case of band pass filters, it will become more selective about the signals for the particular range of frequencies. So we got the first equation for bandwidth in terms of resonant frequency and the quality factor. Similarly, we can get another equation if we use these two terms, if we call them D and E. So by using D and E, we will get another term for bandwidth, which will be R over 2L plus R over 2L. So that will give you R over L. Now we have two equations for bandwidth, and from there we can calculate another term for quality factor. We already know that Q is equal to omega naught L over R equal to 1 over omega naught RC, and from these two equations we can calculate R over L is equal to omega naught over Q, and Q is equal to L over R 1 over under root LC, and Q is equal to 1 over R 1 over under root L over C. So now we have three different equations for the quality factor. In the first two equations we have resonant frequency in that. So if we don't know the resonant frequency, only from the values of the circuit elements we can also calculate the quality factor. Now if we just multiply the two cutoff frequencies, so omega low into omega high, that will give you minus omega naught over 2q plus omega naught 1 over 2q square plus 1 into omega naught over 2q plus omega naught 1 over 2q square plus 1, and we know that a plus b into a minus b is equal to a square minus b square. So using this formula, the above equation will get omega naught square into 1 over 2q square plus 1 minus omega naught square over 2q square. So that will give me omega naught square over 2q square plus omega naught square minus omega naught square over 2q square. So this will cancel out, and omega low omega h is equal to omega naught square, and omega naught is equal to omega low into omega h the root. So what we found that the resonant frequency is actually the geometric mean of the cutoff frequencies. Resonant frequency is the geometric mean of cutoff frequencies. In the today's lecture, we have derived a relationship between the quality factor and the bandwidth, and they are inversely proportional to each other. Then we have proven that the resonant frequency is actually the geometric mean of the cutoff frequency. Now, if I have to solve a simple example using the above formulas, I will solve an example, and in example we have RLC circuit, and the voltage value will be 10 angle 0, the resistor value is 3 ohm, capacitance value is 3.09 microfarad, and the inductor value is 100 millihenry. And we have to find the cutoff frequencies. And bandwidth. So these are the two things that we have to find in this particular circuit. So we will start from the bandwidth. Bandwidth actually is equal to omega naught over quality factor. So we don't know omega naught, and we also don't know the quality factor. So first we will calculate omega naught, that is equal to 1 over from the root LC, and by using the formula we will get 100 millihenry into 3.09 microfarad. And it will give you 1799 radian per second. For quality factor, we know that omega naught L over R, so it will give you 1799 into 100 milli divided by 3 ohm. So that will give you 59.97. So if I'll put these two values in the equation, so I will get bandwidth is equal to 30 radian per second. Now to find the cutoff frequencies, either we can use the formulas direct, like we know that omega low is equal to omega naught minus 1 over 2q plus in the root 1 over 2q square plus 1, and omega high it will be omega naught 1 over 2q plus under root 1 over 2q square plus 1. So either you can use these two formulas directly, or you know that omega naught is equal to 1799, or I'll just take it 1800 radian per second, and we know that bandwidth is equal to 30. So if bandwidth is 30, so omega naught is in the center. Here it is omega naught, and then there is omega high, and then there is omega L. So this whole value is 30. So this is 1800. So there are 15 frequencies above omega naught, and then there are 15 frequencies below omega naught, right? So omega high it will be 1850, and omega low will be 1785 radian per second. So now if you have a circuit given, you can easily calculate the bandwidth, cutoff frequencies, either using these formulas for the cutoff frequencies, or the other formula in which we have resistor, inductor and capacitor, or you can just directly calculate it from the resonant frequency, and bandwidth. So this is a procedure from which you can easily calculate it. So you don't have to do the calculations here. You know the omega naught value and the bandwidth, and you just divide the bandwidth into half and add it into omega naught. That will give you the cutoff frequencies, and if you just subtract it from the omega naught, that will give you lower cutoff frequencies. So this was today's lecture, and if you have any question, you can just send me an email. In the next lecture, we'll be start talking about the energy analysis of the series resonance circuits, and most probably we will end the series resonance part of this particular chapter in the next lecture.